Hi, it's Andre again, and we're going to continue our college algebra prep lessons. And in this video, we're going to continue talking about real numbers and classifying real numbers. So I put together a little exercise, a true or false exercise on member sets. So what this first question is asking is 0 in the member set of real numbers? And we could test that out by looking at what classifies real numbers. So what are real numbers? Real numbers are they're natural numbers, they're whole numbers, they're integers, and they are rational numbers, and they're also irrational numbers, which we denote by I. Okay. So, in order to prove that this is true or false, we're going to have to find a 0 in one of these member sets. So in the set of numbers of natural numbers, we know that there's no 0 in here because it starts at 1 and goes to infinity. But here, in whole numbers, we know that whole numbers has a sequence of 0, 1, 2, 3, all the way into infinity. So since there is a 0 in this member set, this statement here is true because 0 is in the member set of real numbers, so that's true. So we just denote that by the letter T here. Let's move on to the next problem, which says pi is in the member set of Q, which Q is rational numbers. So first of all, let's look at Q. What are rational numbers? Rational numbers are numbers like 1/2, 2/3, and eventually take the form of A over B, where B, where B is not, that's a comma, B is not equal to 0. And also, rational numbers can take the form of these repeating decimals, which can look like 0.3333333, and does that forever. So, pi. Pi is what type of number is pi? Pi is 3.14 and just continues on for infinity. Let's look at pi again. So pi is 3.1415926, and this, if you recall from my previous videos, I said that this 3 is rounded. Pi actually goes on forever, but the calculator can't go on infinite amount of digits, so it has to round it somewhere, and it rounds it here at the 3. But pi does go on forever. So we have a non-repeating decimal that goes on forever, and that is neither of these. See, this is a decimal that repeats forever, and this is some form of a fraction, A over B, where B is not 0, and pi isn't one of either of these. So we could say that the statement that pi is in the number set of rational numbers, this is a false statement. So we could just denote the letter F. Okay, and let's look at number 3, where it says where R stands for all real numbers and Q stands for rational numbers. It says the member set of all real numbers is in the member set of rational numbers. So if you think about what this is asking, it's saying that all the numbers that are encompassed in real numbers are in this member set. So I could find all these numbers in R in here, in rational numbers. And as we recall from above, real numbers includes natural numbers, whole numbers, integers, rational numbers, and irrational numbers. And it's saying that all these numbers are included in this rational numbers. So I could find all the numbers in here, I could find them in here. And is this statement true or false is what we're trying to figure out. So, knowing that Q, what is a rational number? Rational number, as we said here, is A over B, where B isn't some sort of fraction, where B is not equal to 0, or some sort of repeating decimal. And we know that from the previous problem, or just from reasoning itself, that irrational numbers are not rational numbers, because irrational numbers are a non-repeating decimal, like pi, like square root of 2, which is 1.4 and goes on forever, non-repeating. So we know then in all these, which are real numbers, that irrational numbers are not found in here, in rational numbers. So we could state that this statement is false. And let me just give another example of why this is false. Because rational numbers, Q, are numbers like this above, like A over B, where B isn't equal to 0, right? And these repeating things. I don't know why I'm writing this over again, but I am. Okay. And in the real numbers spectrum, which are all of these numbers here, these are all included in real numbers, we know that I, which are irrational numbers, are numbers like pi, which are 3.14, and then continues on non-repeating forever. And these numbers are not found in this number set. So this is false. I just had to explain it again because I just want you guys really to get this concept. So let's move on to number 4, which states irrational numbers are not in the member set of rational numbers. And let's see, if we took all of our irrational numbers, which are 3.14, remember that, square root of 2, 1.4, and it's saying these are not in the member set of rational numbers, which is true. So, because we just actually proved that here, that that was the defining principle that caused this to be false. So this is true. This is true here. Okay, and let's look at the last example where it says square root of 5 is in the member set of rational numbers. And let's see what square root of 5 looks like. What does square root of 5 look like? Okay, so we have 5 square root. So square root of 5, it actually looks like it goes on forever, non-repeating. So if it's I know it doesn't look like it goes on forever, but you have to remember that calculators, they can only display so many digits because they don't have an infinite amount of space to display digits, so they can only go so far. And so we know square root of 5 goes on forever, non-repeating. What does that remind you of? That reminds me when I think of that of an irrational numbers. So this, if square root of 5 is an irrational number, and we'll say that is I, and what this is saying, it's saying that 5 is in the number set of rational numbers. So if square root of 5 is an irrational number, then it will not be in the irrational numbers. So this statement is false.